Hello, everybody, and happy 2017. Welcome to our first hangout of this year. In fact, it's our Footsteps to Mars hangout. My name is Tony Darnell. I run deepastronomy.com, and we are starting a new year off, I think, with a really great hangout to discuss more about what we went into last month's hangout, which, if you'll remember, we talked about ISRU, which stands for In Situ Resource Utilization for Mars Exploration. And so the story behind this hangout's a little bit interesting. Last month, we were doing our Footsteps to Mars, and there was this guy on there on the live chat who was really doing some great, was really adding great things to the chat discussion. And so we got to talking over email, and I invited him here with us now, and he invited our second guest. So I'll introduce our guest here in just a minute, but this is going to be a bit of an extension of what we talked about last month when we talked about ISRU. We're going to go a bit more in depth, but Bob had the great point there's some things that we need to consider before we ever put bootprints on the surface of Mars. We're going to talk about what some of those are here in just a minute. But before I get started, let me introduce my longtime co-host and friend who helps me wrangle these, Dr. Harley Thronson from the NASA Goddard Space Flight Center. Hi, Harley.
Yep, good afternoon. Once again, Happy New Year.
Happy New Year to you too. And you are currently at the American Astronomical Society's meeting, right? They have this every year.
Every winter, twice a year. The big one is wintertime. We are here in actually very attractive Grapevine, Texas, which is a nice part of the world, nice part of Texas. It's sort of a suburb of Dallas-Fort Worth Airport.
Yeah, and for anybody who's followed Space Fan News for any length of time knows that the reason it got started was I wanted to report the news from that week, that meeting, the winter meeting, way back 6 years ago, and that's what started Space Fan News. And so got another one coming up tomorrow where I'll talk about some of the big news that's come out of this week's meeting. And Harley is there right now enjoying the announcements and stuff firsthand. And I've gone to several myself. We've even live streamed from them a couple of times as well. And speaking of the American Astronomical Society, these hangouts are endorsed by two AASs, the American Astronomical Society, which we just talked about, and is having their annual meeting in Texas right now, and also the American Astronautical Society also endorse these hangouts as a way to get as an avenue for the membership of those organizations to talk about their latest research and work that they're doing and get the word out to the general public. So we're really grateful for their endorsement. And while these hangouts are endorsed by them, the opinions and views expressed in these hangouts are not necessarily endorsed by those organizations. So be careful, guys. Don't be expressing views that aren't
Yes.
properly.
No views are not permitted here.
That's right. Don't be giving those unendorsed views.
In fact, actually, just the opposite. Although not endorsed by the two AASs, views are very welcome.
Yes, they're definitely welcome, but they're not necessarily endorsed. Okay, so please, we are live right now. We are here, and we want you to interact. The best way to do that is to go to deepastronomy.com/live. I have my chat window up right now, and I'm looking at people joining. I see some people now. We see Hans smiling and R. Rashido and all kinds of people. Amber Britt NASA has joined. Larry Keese, lots of people here. So ask questions, comments, and I will read them out as we go along. So let's get started. We are talking about Mars and getting to Mars. And our guests today are both from NASA's Langley Research Center. I have with me Dr. Robert Moses. He's a space engineer. Hi, Robert. It's good to see you live and in person. You were on the chat last month.
Thanks for having me, Tony.
Yeah, you're welcome. And thank you for taking time out to join me. And also is Dr. Komar, and he is a space architect. And he's also from NASA Langley. Hi, Dr. It's good to have you. Thank you for joining our hangout. So as a bit of a background, there are two big ways that NASA and others are looking at getting to Mars. We all know that we've heard about some of the private efforts by Elon Musk and things like that, but NASA has been considering two main ways of getting there. One of them is sort of this using the Space Launch System to go to Mars, walk around, do some stuff, sort of in an Apollo-like format, and then come back. And then the other way that they're looking at going to Mars is using a more sustainable approach, using a more, I guess it's sort of a colonization way where we go to Mars and sustainably live there for a much longer period of time. And that's and part of that is called, we talked about this last month, in situ resource utilization. And this particular, we're going to take this a little bit further, and we're going to talk about, I guess, Bob, maybe you can talk a little bit more about this. It's called ISRU to the wall or something like that. And
Right.
so Bob, tell me, which of these approaches are you at NASA Langley working towards, and which do you think is a little more, I guess, practical?
Yeah, I prefer the living off the land pioneering, or the latter one that you were mentioned, rather than just a quick trip over for, a month and then right back. So in terms of making Mars hospitable and safe, I feel I've got my philosophy on how we should do that. And I think what we should do is exploit the abundance of resources there robotically, prepare a place for them, for the crew before they leave Earth, and then have everything up running and ready for them, and know that it's going to be reliable and safe before the crew ever gets there. That involves stockpiling resources. That's where the ISRU comes in, and Jerry and Diane talked about that last week.
That's right.
So what we did, this ISRU to the wall, this is something that started in 2014, and what we want to do was look at 3 cases of ISRU, and that's what that paper is on that you mentioned earlier, the ISRU final. One was no ISRU, just everything's expendable. Then we looked at a case called light ISRU, which was basically just manufacturing or processing with the minimal amount of ISRU for the consumables that the crew would need and for fuel to get home, and a few other little things like that. And then the extensive ISRU was really the gloves off, clean slate. What all can you do with the resources there, such as make plastics that will all help towards achieving Earth independence, breaking the logistics train back to Earth. And so the team looked at that, and that one was very favorable in that presentation. We also showed the increase in cost, or the delta that would be required to make all that come together. And then we normalized that by the number of crew days on the surface. And when you do that, that's a sustainability index, if you will. And the extensive ISRU looks very promising.
So I'm going to show this. This is a quick little one of the slides from the talk that you gave, or that you had shown me to. By the way, folks, this PDF file is available for download. It's on the description box below, but just click on it and you can look at these a little bit. Hopefully it's not out of focus, but maybe on your own computer as we're going along. But here is sort of a little graphic of what you're talking about. On the one hand, if we just try and shoot the moon and go like we went to Apollo, we're kind of looking at this sort of right-hand picture where we got to carry everything with us. This guy has all the water he's ever going to need on it, and all of this other kind of stuff. And then the other way we're looking at going to Mars is here on the right, which is using the resources that we find. We don't have to carry. You don't see her being burdened with a huge keg of. I hope that's a keg.
Yeah,
of
I don't
water.
think that's water.
Yeah, I was just thinking about it as I talked about it. Yeah. So
it is crew consumables.
Yeah, crew consumables. Yeah, that big keg of beer looks definitely well. So as opposed to bringing your own beer, you have to brew it there on Mars. So so that's sort of what we're talking about here, isn't it? We could bifurcate at an early stage. And Bob, is this what you meant when you say before we ever go to Mars, there's some things we have to consider first? Is that what you meant?
Right. So there's what we did in the study was to break this Mars campaign for each of the 3 cases of ISRU. We broke the campaign into 4 phases. One is the prepare phase, where the robots get their task accomplished without humans in the loop. The humans can monitor it just like you would normally, how we monitor data coming back from our rovers or landers. And then the second phase is where it's the found phase, and that's where the first crew goes. And then the third phase is where additional crews go to Mars, and that's the expand phase. And all these are taking about a decade to 15 years each phase. And so the sustain phase is that we're pretty much Earth independent. We've got all these ISRU processes. There's a chart in there. I can't remember whether it's chart 9. It talks about the types of ISRU we're considering, where you have the ability to exploit the resources there to make just about anything and everything necessary there. And so that's what.
Is it this one?
I've been talking about.
Put this up. Is it this one? Is it that?
You've got one. I don't. Okay, next one.
The next one. Okay, let me just move it over. That one.
Right. So, whoop. Yes. So what we showed there in the green are the what we would consider. These are the ISRU processes that we considered in this study, and we varied the degrees at which these are turned on or turned green. The extensive case, all of these are green, and that's the case where you're manufacturing on the planet. Now, if you go back a few charts, it's important that you understand the phase is which, even that one's a good one right there. You can bring that one up, Tony.
Yeah, I did. It's up.
Oh, there it is. Okay, I can see it now.
Yeah, just click on my thumbnail if you're not seeing it big.
Okay, so let me put my eyeballs on so I can read it.
Oh, those are cool.
So yeah, these are
Mars
size. So the prepare phase is the one where we do the capability demonstrations for ISRU and other surface systems. No crew has left Earth yet. This is just doing the propellant and water ISRU, getting the habitat up and running, basically covering up the habitat, burying it for radiation protection and thermal protection. And then it's not until we start transition to the found phase that we start with the really big stuff, but everything in the prepare phase is done robotically. And it's to stockpile the things that we know the crew is absolutely going to need, which is propellant and fuel, and it's stockpiled. The habitat's up and running, so once they get down to the surface, they're pretty safe as long as they can get into the habitat. Now, one key element of this, and this is where DR has really shown his expertise, is the reusable lander MAB, where it uses ISRU fuel to bring down from low Mars orbit all the things that have been parked there by aero capturing so that we can build up the surface to make it safe for the crew. And DR will be able to go through his lander concept, which I think is extremely brilliant.
Okay, we will talk about it, but before I leave this topic, so right now I'm just kind of setting the stage between the two big ways of getting to Mars. You guys are obviously at Langley are proposing we do this covered wagon colonization approach to get to Mars. The other way is using the Space Launch System and doing these Apollo style missions out there. Do either of you know, and since you're in, I know that you're working in the one camp, but do either of you know how seriously NASA is considering the other option, these sorties, these one-shot moon landing kinds of missions where you carry everything with you, you land, you walk around for a couple of days, and then you come home?
Well, I can answer. I can try to address
Okay.
that.
Okay.
Because I've actually supported both sides of that. The Evolvable Mars campaign is a term you may have heard. That's been some of the efforts that have been going on within the agency.
Evolvable Mars campaign. Yep.
Evolvable Mars campaign, and it's been our over the last couple of years been our main effort to architect a plan to go to Mars, and it's from that effort the Journey to Mars document came from, and the whole philosophy of pioneering. However, I would contend that what we have actually done, because we were driven by the need to get humans to Mars as soon as possible, which was mandated, by the president back at Kennedy Space Center, by the end of the 30s or in the 30s, that really drove a lot of the decisions on what the systems would look like. It really, by putting a time frame on when trying to get the crew there as quick as possible, we wound up with a very expendable staged architecture, a lot of stages that we throw away along the way. And in the end, you wind up being able to accomplish a sortie. And the hope is that over multiple sorties, you can begin to build up an outpost or a settlement. But each one of those is about the same cost. From an affordability standpoint, you're paying about the same price for all of those because you have to rebuild it every time. You have to rebuild the transportation systems from the launch vehicle all the way to the landing systems at Mars. So that's where we started beginning to consider alternatives of what if we started looking at reusability? How does that affect affordability? And that's in the IRCU to the wall study. We really found that it's a very large lever. Has a huge influence on not your initial costs, but your long-term costs in terms of achieving your end state of a settlement of some size. With some degree of Earth independence.
Right, because if all you did was send somebody out there in a sortie and then came back, you've spent a lot of money, you've done that, you might even have done some science, but that's really all you've got to show for it. You might have some technological spin-offs, things like that that are valuable, and of course we all have additional pride.
Choose to go back to that same site again, but like I said, you'd have to rebuild the entire system that you've thrown away to do it all over again. So,
So there's two ways to spend your money. You can either do it for this, or you can look for the longer term and get these more bang for your buck. Is it more bang for your buck to do it this way? The longer term colonization scenario?
Well, it depends on what your goal is. I mean, if your goal is to plant the flag and claim victory, and there's some political reason that that we wanted to do that and be the first to get there, like Apollo was, then that's great. That would be the way to do it. It was a race. We needed to get there as fast as possible. But if it's our goal that we want to expand human reach into the solar system, not just temporarily but permanently, then I would contend you would make different choices in terms of what technologies you invest in, what systems you invest in, how much effort you put into things like reusability, autonomy, robotics, ISRU.
I know
all those things that are going to help us become a Earth independent.
And so you've really hit on the heart of it here, DR. You really have. And Harley promises me that one day we're going to have a policy person on here. But it really all comes down to what is our goal going to be to get to Mars? And are you guys at Langley sitting there in your meetings and going, if someone decides that our goal is a long-term sustainability approach, boom, we're ready to go. Here's what we want to do. Is that what you guys are doing? Because we don't know yet, do we?
No, we don't. And the hope is that with a new change in administration, that there may be change in directions. And certainly we want to put these ideas out on the table. But yes, if there is a change to move that direction, we certainly have some ideas which we think are gonna help us in that to move in that direction.
Okay, well, great. So I want to move on to the next topic, and before I do, I just want to take a quick break and say this is a Footsteps to Mars hangout. We have these every month, and we want you to interact with us at either deepastronomy.com/live. You can also use the hashtag Footsteps to Mars, and I'm looking at that on Twitter. My guests are Dr. Robert Moses from NASA Langley Research Center. He is a space engineer, and also with me is Dr. Komar also from Langley. He is a space architect, and these guys have been thinking about getting us to Mars, and we are talking with them about some of the things they're working on to get us there. So please join us in the discussion. I'm seeing a lot of questions, and I will get to them in the live section here in just a minute. Okay, so we talked about the two big ways of getting there. There's the moonshot approach, and then there's the colonization approach. I want to talk a little bit about site selection. And Bob, I think that's something you've been working on quite a bit. First of all, let me just ask you, is there a difference, regardless of the approach, regardless of our goals, that has an effect on site selection, right? How do you think about where are we going to put people on Mars?
Yeah, so I'm loosely connected to the Human Exploration Zone studies that are going on because of my contacts with folks who are at the heart of that.
Yeah, we did have a hangout on that, one of our first ones. Go ahead, I'm sorry.
Okay, so where they are now is over 50 sites have been identified as potential human exploration zones. And the link I sent you earlier. Yeah, I'm waiting. Let's see.
Let's click on my thumbnail.
Yeah.
It says potential exploration zones for human missions to the surface of Mars.
Yeah, I'm clicking on your thumbnail and I get a blank screen.
Okay, try a different one and then go back to me and see if it refreshes. We are at the mercy of Google, folks.
Yeah, that's like. Well, I'll just talk about.
Okay.
Yeah, it's not coming back.
Can you see a DR?
No, I cannot.
All right, let's try this again. Let me stop my. Can you see me?
Yes.
Yeah, there you are.
Okay, so now let me try it again. One more time. Share. Now, do you see this?
There.
Okay,
Yeah.
there.
Yep.
There now? Okay.
Right.
All right.
So this is one of the figures, and this shows across the planet about 50 or so, a little more than 50 potential human exploration zones. If you'll bring up the other figure that was out there on that journey to Mars, it shows kind of what the little exploration zone circle would look like and the types of things they're looking for.
The web page. Hang on.
On that web page.
Okay, that was a tiny image. So let me just pull it
Right.
up.
So yeah, I'm not sure how it's going to look.
Let me look here. Where to go?
But to be able to look, yeah, what you're getting ready to show is an example of what they would like to see. Right, that one would like to see in a human exploration zone. There's the scientifically rich area where they don't want it contaminated. Then there's the sites where water would be allowed to be extracted and other things will be allowed to be extracted, other resources for the benefit of the crew.
Okay, so hang on, Bob. Let me just interrupt. This is an example of a typical site consideration. Okay, go ahead.
Right. So these are the type of things they'd like for each human exploration zone to have, or at least the one that's down selected, or the handful that are down selected. So, so this is all notional. We don't really know that what they showed there is actually that. We just haven't done the due diligence necessary for that. So what we're looking at now is to try to understand where's the subsurface ice and where are the hydrated minerals. So we're trying to check the box on the sources of water first, and also, but to be able to to really map out a site would require an extensive, investigation by rovers that are sterilized. And that's a lot of area that would be asked for a rover to look.
Okay, so what are we looking at with this big red circle here? How big an area would you say that is? That would be what you're talking about? The rover would need to go around here.
Well, it'd have to search in there and find the things that we're looking for.
That's 100 kilometers, if I remember.
Yeah. Okay.
Yeah, it's substantial.
All right, so we have a resource region of interest. We have a science. We have all of the science and an exploration zone. But these resource ROIs are what you're talking about as far as where there might be water or some other resource that can be used while the people are there. Correct.
For the benefit of even before the crew gets there, that's where the autonomous ISRU processes would come in and start cracking water and cracking CO2 and making the things that the crew would need before they come and get the habitat up and running. And where the habitat would be allowed to set within that circle is a question as well, because wherever you put the habitat, you can it will devalue the scientific pristine or integrity of that area, because once you introduce a human, you don't know that you're finding something that was naturally occurring there now.
That's a good point.
So
okay,
that's where the planetary protection folks are looking at policies.
Right.
How you do that.
And so for the science use cases where you care about doing some science, that's really important, isn't it? Well, even I guess for resources too, but mostly science. You don't want to be contaminating everything with stuff that we brought, like our rovers and things like that.
Right.
So that's a big effort, isn't it? Getting these things sterilized or what they, ready to be used on Mars.
That is correct. And the bigger the rover is, or the bigger the lander is, the more difficult it is to meet the sterilization spore count. So there's big engineering issues involved with going to human scale landers and being able to make sure that they don't introduce something or can't contaminate. And so that's on the plate of COSPAR to understand, where the balance is between making it happen versus what can we allow to get contaminated, but only as long as we know it's not going to be transmitted around the whole planet. So, and again, the idea is to find the sources of water that are easily accessible, that perhaps would not lead to contamination of a bigger pocket of Mars.
Yeah. So, and we've talked about some of this before, folks, where we've talked about this. There are treaties involved and things where you want to be careful about what you send into space and how you go into these other bodies in the solar system. And in fact, that's going to be especially important in the coming years as China and India also gear up their space efforts. And so they've got plans, and in the European Space Agency has plans for Mars rovers. So all of this is extremely important stuff, especially when one is trying to do science. So getting back to, you mentioned this earlier, Bob, and now I want to get DR to comment on it. And that is these, you've been working, well, or should we do the robotics first? We should probably do the robotics first, because we got to do some preparations to get us to Mars, and that's where these robotic devices come in. What are the big areas that these robotic vehicles will be working in? They'll be sending habitats out there, presumably. They'll probably also be sending things like fuel and stuff, but will there be any manufacturing capabilities? What are some of the things that we'll be sending robotically?
Right. So if you go back to that chart we showed earlier where it was prepare phase, the things that would be sending there first is whatever's necessary to, say, ditch and cover an inflatable habitat under 3 to 5 meters of regolith. That's the habitation bullet underneath the prepare bubble.
Okay, let me get to that. Hang on, just let me pull it up. Is it this one? I hope it is. Am I right? Is it that one?
Let me toggle here. No, go back.
Go back?
Go back, right. There we go, right here.
Got it. Okay.
So underneath the prepare is a blue bubble capability demonstration. Then look at test demo 4, the bullets under there. So propellant in water. So to be able to make propellant in water or drinking water or whatever, so you got to be able to access the ice or hydrated minerals if you have to, depending on how much energy you have. Propellant is probably going to be methane, which involves carbon. So the carbon will have to get stripped off the CO2 atmosphere using some solid oxide electrolysis system. The hydrogen or the methane will have to come from the water, or either out of the regolith, or I hope we wouldn't try to depend on water vapor in the atmosphere. But then you go through electrolysis system, and then all that would have to go through a Sabatier reactor or something to produce the methane. Then the habitation, already mentioned that, in terms of ditch and cover a habitat and have it up and running, and understand, what are the failure modes while the habitat's up and running and operational, long before the crew ever leaves Earth. And the excavation and burying of equipment, again, is just protecting it from GCR and thermal and micrometeorite damage. So those are the minimum subset. And of course, there's no humans there yet, no crew. So all this has to be done autonomously. So what does that surface architecture and space architecture look like to allow robots at MSL or larger scale to run around within
MSL? Sorry, what's MSL?
Mars Science Lab.
Okay, thank you.
Curiosity.
Size of a Volkswagen Beetle, a small one. What does that look like to be able to enable these things to run around in that small exploration zone? A tongue in cheek about small, 100 kilometers, but that's the minimum set. We're not doing any manufacturing there. We're just making sure that we can do these things that are vital. If you cannot bottle the water and use it for the benefit of the crew in terms of propellant and water, and then later the manufacturing of using plastics, which comes from water and carbon dioxide, then it's going to be tough to sustain crew, and you're back to the initial mission that we don't think is safe.
Well, I can easily see why this is long term, because here you're talking about preparing, and then you got test and demo for all of these things. So
Right.
presumably you're going to send out little test craft to do all this, and then you're going to do the actual thing, right? So
Right. So a chart in there that looks similar to that, and it's got a timeline. There are years across the top. And sustain ends up at about 2070.
that one, no.
Well, that has the years across the bottom, but if you go back,
Yeah, he had one. You had it up.
I think it was 6.
Oh,
yeah, go to chart 6. Try chart 6. There it is, right there. So
oh, I
yeah,
see.
so
The years are crossed up here.
Right. Right. That's
Okay.
2024 is right over the second P, all the way out to the
Yeah.
2070s for the sustain. So, like I said earlier, each one of these periods
Look at
lasts
that, all the way
about
up to
50.
77. Wow.
Yeah, so these are about a
Okay.
15 year period. So to get ready for prepare, we need to spend the next 5 or so years down selecting the technologies we want to get ready to send to Mars in the 2030s, or maybe even a little before, early 2030s, to have them operational on the surface for 5 years before the crew leaves. That way we've bought or paid for safety through reliability. And if we're exploiting the resources there using ISRU processes that really truly prepares the site robotically before the crew ever leaves Earth, then we have a pretty good chance of reaching the found phase, which is when the first initial human surface presence is shown there.
Were we looking at mid 30s, 30, mid to late 30s?
Right. So there's by the by the 2030s or 2037, I think it's kind of the number that's floating in everyone's mind as a potential target for the first Bootprints. So now this is where there's a key thing to be able to build up this, because even for the prepare phase, even the habitat is a lot more than what the Mars Science Lab is in terms of mass. And this is where DR expertise really came to bear. And I think this is probably a good time to talk about that. But the idea was to park in Mars orbit somewhere around 60 metric tons using aero capture. But then how do you get the 60 metric tons down? Well, if there's a way to use a reusable lander MAV that can take the payloads down in 15 to 20 metric ton chunks, then after 3 or 4 trips, you've got everything you need down there to kick off the prepare phase and do a really good job. Now, what that would also do is you now have a lander for when the crew gets there. You've already certified to some extent a lander that you know is going to work because you've demonstrated it at Mars. So your confidence has increased substantially.
Okay. Well, since you brought it up, I think you're right. It's a good time to talk about. So this is in the next phase after prepare, and this is what you've been working on, right, DR?
Yeah, this what we're looking at here is the 2014 study, and we've come a long way since that time. And some of the updated work on a reusable lander that we've been calling Hercules was on a Space Review article back in October, and we have a graphic that you can bring up to kind of illustrate that. But I guess before we get into that, one thing I would like to say, though, one thing that I think has changed since the original 2014 study relative to where we are today is that back in the 2014 study, we were making the assumption that we landed the ISRU plant with the ability to fill up the lander and be reusable on the very first landing. Over time, we've kind of thought about that a little bit more, and that may not be a reasonable thing to do. May not be a reasonable assumption that we can be reusable right out of the gate. If we can, that's great. But if not, we anticipate that the campaign may actually have it's part of that prepare phase, and as part of the verification and validation or certification of that lander for crew, a few or several expendable flights where they would land infrastructure along the way.
Okay, so hang on. So I want to make sure I'm getting this right. So you're saying that we gets into orbit, it deploys, like this, it goes down and then lands, does whatever offloads whatever it's going to offload, whatever it's carrying, and then you're saying to be reusable, it has to have either enough propellant on board, 74 tons it looks like, or create it somehow. And you're saying,
and what we were doing, that first 20-ton landing, that lander would go down. It had 20 tons of cargo. That cargo was the power and ISRU and liquefaction and storage systems to manufacture that 74 tons of propellant so that we could turn around and go back up and get more payload.
And you're saying it's optimistic to say that the very first shot around, you're not going to be able to necessarily, it's not going to be able to
That's
do all
right,
that
because if we
out.
stumble at all, then the whole campaign comes to a screeching halt. We have, you're counting on the very first lander to work as advertised. And, we've seen in the commercial world, even Elon Musk didn't attempt to land the Falcon 9 back on the pad or out on the barge on the very first time. He planned for it from the get-go, but he worked his way to it and demonstrated increasing capabilities over time. And eventually he got to the point where he was successful in landing and reusing systems.
Okay, we're getting... Okay, you're right, and I see your point, and it's a good one that we need to be realistic about what these expectations are going to be the first time around. And I'm glad you guys are thinking that way. But the oh shoot, I forgot where I was going with this. Oh,
actually, I've got a question then. I can fill in, Tony, possibly. Okay. So there's been, and you folks obviously have been thinking about this for some time. Even before the first block, the first early exploration block that you have on your plan, you're gonna have to develop the technology, test it out here in the lab on the Earth, and so on and so forth. There are folks who are advocating, even before one goes to Mars, test out many of the capabilities, not only the ones you've been mentioning, but others, on the lunar surface. Have you folks given thought to, before going to Mars, where Earth, free space, lunar surface, you would want to test out your capabilities, the technologies?
Recently we have. When we did this original 2014 study, we were kind of set our sights going directly there, working the technologies, demonstrating them either at Mars or on Earth. Lately we've begun to consider lunar proving ground as a place where we can prove out some of these capabilities.
Now
we're migrating our thinking in that direction. Yes,
that's NASA speak, proving ground for the orbital vicinity of the moon. Usually, have you given thought to the value, if any, of the lunar surface?
Okay, yeah. Well, I've been thinking the lunar surface as well as a proving ground, but that but yeah. So what we were thinking is that you could utilize this lander designed for Mars. But maybe stripped down, a little less capability because you don't need thermal protection systems for entry. But you could prove out quite a bit of the system in terms of its operation of the engine systems, propulsion systems, tanks, cryogenic fluid storage, and so forth. At the moon, while also using that same system to deliver important payloads to the moon. Right. So it could be utilized, while you're in the midst of trying to prove out and certify that vehicle, you are using it along the way, maybe in an expendable mode, or I don't really like to call it expendable because we like to say repurposed. We would repurpose part of those landers for other things later, but you could do that on the moon, and our story with respect to that is a little bit soft at this point because we've only recently begun thinking about that, but and that very well could work out. Yeah, it might make a lot of sense to do a lot of that at the moon.
Yeah, just one quick point about that is that the abundance of water on Mars is not there on the lunar surface. So that's that would have a different. It would constrain exactly what is tested on the lunar surface.
Right. But some things you can do, like maybe the mining stuff, the digging hole stuff, all of that kind of stuff you can use and test. Okay, I want to remind you.
Right.
I just want to remind everybody that you are watching our Footsteps to Mars Hangout. We have these on the first Thursday of every month, and my guests today are both from NASA's Langley Research Center, Dr. Robert Moses and Dr. Komar. These are space engineers and architects, respectively, who are thinking about getting us to Mars. They're working on plans to get us to Mars. In particular, they're looking at the colonization, living off the land approach of going to Mars. And so my question to both of you here now is, I know you guys are thinking about this. You're having meetings. You're making drawings. These plans look extremely reasonable. Obviously, they have to be tested. And maybe this is a loaded question. If you don't want to answer it, I guess you don't have to. But are you guys given any resources to make this happen, or are right now is it just are we just thinking about it? You guys given any resources to actually build some of these things, or is it no one or are we at that point where people are deciding how we want to go to Mars still?
So,
Bob, I'll let you answer that.
Yeah, I'll answer part of it.
Okay,
let me answer part of it.
It's politically sensitive,
Langley,
I'm sure.
Well, where Langley is in the middle of this is the architecture and using some engineering to, I guess, make the architecture or whatever comes up out of our paper studies and analysis have some feasibility or reasonable estimate. It's the other centers that are really building a lot of the hardware, like Johnson Space Center, for instance. They're pretty much the lead center on the ISRU and human exploration aspects. And Langley is lead on doing the architectural studies and tying all these things together and knowing from a strategic and campaign perspective where certain things get turned on and how to make the investments for the agency. Where the agency should start, or might want to start spending money to develop X, Y, or Z. So, I don't need a lot of money to do this work. I've been thinking about it, and like Dr. mentioned, we've got a new administration coming in, and we'll really have to see what that's going to do to the thinking we've had in place for the last 3 or 4 years. See if that's going to change drastically, or
yeah. I'd ask you if you had any thoughts or predictions, but I don't think anybody can predict anything right now. So.
I'm very happy to be here and work for NASA and our country.
Good answer, Bob. Okay, good answer. I'm just happy to be here doing my job.
And I probably speak for Dr. to some extent on that, but he's got his.
Oh yeah.
Go ahead. I want to get to some comments that I'm seeing on the chat. But before, I have one last question for both of you, and that is, with this colonial approach, this sort of, we're going to go and set up I don't want to call it a colony. Well, it is a colony. It's a human colony. And we want to stay there for a very, very long time, as long as we possibly can. Are we worried at all about trashing Mars, or are we just going to go and start using natural resources like we did here on Earth and just kind of build? I can imagine we start putting nuclear reactors up, we start putting, we start digging big holes and mining, and all of a sudden I'm seeing these big mounds with tailings everywhere. Are we worried about that at all yet, or are we just trying to get there? You guys thinking about that?
I'll defer to the engineer.
Okay.
Yeah, I have been thinking about that, and that was one of the reasons I wanted to get involved with the COSPAR policies.
Tell us what that is, please.
The COSPAR is the Committee for Space Research, and planetary protection is one of the, I guess, the charters or items they have. It's a space policy for planetary protection. And recently I got involved with that and have been contributing for the last few months on how we address not trashing Mars, but allowing ourselves to become a 2-planet species or multi-planet species. And while at the same time preserving the scientific value of understanding what happened to Mars and is there really life there? And if we find life, did we bring it or not? So yes, definitely it's on my mind that we don't want to go trash the place. There are areas where we would love for it to remain pristine for centuries, not decades.
Right, but there's this one. I'm going to bring this one picture up. I hope I can find it quickly.
But it's very expensive for us to send so many people that within 100 or 200 years we have trashed the planet. I think if we can put planetary protection protocols for contamination in place, I think this is going to take a long time. There'll be a lot of science.
Okay, so here's a schematic that you guys had sent me, and I'm seeing here there's a lot here, obviously, of what a typical colony might look like. But the part that I'm looking at here is this underground habitat. There's a lot of digging going on in here. We got
that's notional. That's notional.
No, I know that, but I'm just wondering. This looks like a pretty big footprint on Mars' surface. So I'm glad you guys are thinking about it, but this has to add to the complexity, right, Bob? I mean, it's one thing to go and dig a hole and mine some materials, but it's one to do it responsibly. It's a totally different technology.
So this was you're right, Tony. This is just a cartoon. What we expect to do is, if we're going to a place where there's subsurface ice, we can expect a meter or so of overburden. So we've got to remove that overburden anyway. So if we're going to be ditching or taking an excavation tool along, maybe it's a chariot or an athlete rover with a blade, a bulldozer blade or something. So we're going to ditch and then cover up the regolith we took off the top of the ice to be able to expose the ice for ISRU excavation or extraction processes. That's the regolith we'll put over top of the habitats and these other places. And I think the underground places are really nothing more than inflatable fabric structures with and some internal skeleton that will prevent a collapse. But I think this is an exaggerated cartoon of just how deep we'd be going.
Sure,
now,
sure.
There are other places like it, and that was certainly true in the Mars series, where you can get underground naturally, and those are in lava tubes that have been vacated. They're no longer active, so the volcanic activity is dormant. So, but they're hard to get into in most cases, and they're jagged. So that's not our primary. In my opinion, it's not our primary source of getting down beneath 3 to 5 meters of regolith for galactic cosmic radiation protection. I think the ditch and cover, because we have to uncover the ice that we plan to use for ISRU. So why not go ahead and just continue to cover up inflatable habitat?
Sure. Okay. Well, and I brought this cartoon up for another reason as well, because I want to get to Phildo Daggins. nice handle on the chat. He's asking my question whenever it becomes relevant, and it's now relevant. How will they handle the issue of radiation? Is this one of the defenses you guys are thinking about for helping protect people from radiation? So building it underground.
Well, right. So 3 meters of regolith provides sufficient protection from galactic cosmic radiation. If we're using nuclear power on the surface, we'll have to make sure that it's behind a big berm or from the habitat or where the crew would be going. And also, we want to make sure that any thermal activity of the surface power isn't going to, help cause life to suddenly pop or something start growing. So that, again, this planetary protection and radiation are two of the big issues. But again, a meter of water or 3 to 5 meters of regolith provide plenty of radiation protection. Okay, so the one more thing I want to put up here was, well, I can't find it now, but one of the things that you were looking at, I know where it was. It was in this past one here. It mentioned, here we are. Sorry guys, I'm just wrangling technology at the same time. This slide here, where we were talking about deploy, and we talked about the Mars lander, the Hercules truck. You're also looking at what is that? 100 kilo? Is that kilowatts? KWE?
Yeah, that's electric. Yeah,
that's supposed to be
kilowatt electric.
Kilowatt nuclear reactor.
To manufacture that, the large amounts of propellant at the rates that would be needed, you really are going to need large amounts of power.
Right. And are you guys considering nuclear because of the energy density, a smaller footprint? You need less of it to create a lot of power, like for example, wind and solar, I imagine. are very difficult to do on Mars for a lot of reasons. But is that why you're looking at nuclear as the primary power source?
In terms of the bang for the buck, given that we need that much power and then some, I mean, as the base grows and as it evolves, it would require even more power to drive all of the ISRU processes, manufacturing processes. And
would you be thinking of getting the fissionable material there on Mars as the uranium, or enriching it there, or are we going to bring it with us?
Oh, it'd have to be brought with you guys.
Okay, so the first thing that comes to my mind then is remember all the crap that people gave probes like was it Galileo and Cassini? They had these, and Voyager, they had these little thermonuclear reactors on them, and were launching them, and there were all these people very nervous about how are you going to get past that obstacle? Is that just a political one of launching enough material to make a 100-kilowatt nuclear reactor?
Well, there's not that much nuclear fuel that's required for a reactor of that size. That's plenty of fuel from what my knowledge is of ISRU. Our colleagues here are exactly right. You are going to need quite a bit of power, but 100 kilowatts electric is not a big nuclear reactor.
So we're not talking about, well, we're still talking more than what goes in a typical probe though, right?
Oh yeah. Well, that's yeah. Those are also.
So that was my point. That's more than what we get for Cassini or whatever. You know, these ones that have these.
But that's a different nuclear power source.
Yeah, it'd be interesting to see how that plays out.
Sounds like this topic and the last one we were just talking about are great for your next guest, your space policy.
My policy person, I know, Harley. I know.
I keep promising policy. I keep promising policy. One of the reasons we're waiting is delaying that is we're waiting for the new administration. So we'll have some things substantively to talk about, not speculate about.
Okay, so Dave Murrow is asking, and I'm not quite sure I understand this question, but I'll ask anyway. Have you considered short sorties from a permanent human presence in Mars orbit? Oh, I see. So yes, have you considered going into a long-term Mars orbit capability and then doing short sorties back and forth from there?
So not going down to the surface at all?
No, going down, but just from orbit, and then not staying for a long time. In other words,
you're in orbit for a long period of time. The human sortie from that position, you do few day or several day human sorties.
Right. Is that something, to me, that doesn't sound any different than a sortie period, because you still got to carry everything with you, right?
Well, yeah, but you can make the surface systems a little bit smaller. There could be some savings there for your short crew surface stay. But then it means you have to have more infrastructure up in orbit to support them while they're there.
Right.
Because they're still going to stay the same amount of time in Mars' sphere of influence.
And you're probably going to need artificial gravity if you're going to be up in orbit for long periods of time like that.
That's right. So that adds to the complexity of the mission in a different way.
Spinning a large spacecraft is going to be very difficult.
To answer Dave's question, I think there have been some looks at that. And Evolvable Mars campaign, they were doing something. Well, they were actually doing kind of their first mission was to Phobos, and they were staying in orbit and then doing a sortie out to Phobos and back, and then maybe even doing some telerobotic exploration from Mars orbit as part of that. So there has been some looks at that, and there certainly I could envision including something along those lines, especially in the preparatory phase, like we were talking about, where maybe we want to, rather than autonomously control or set these robots free to go explore this 100-kilometer space, maybe we're telerobotically controlling them from orbit while they're looking around at a site because there might be things that they can't see that we would be able to see if we had, telepresence there.
Right.
And if you're using hoppers that were doing nothing more than just burning carbon monoxide and oxygen, didn't need access to the water, they could refuel without having to get water, then maybe that's a way you can really do some due diligence without even having to depend on a rover. You just have little hoppers that go and look, and that's another thing that DR's concept would allow in a smaller scale.
Okay, I want to get to one more comment before I have to go, and that is from George Caldwell. There's a lot of concern about radiation because it's been in the news a lot. We talked about any people that go to Mars getting all these brain conditions, things like that. He's asking, my question regards radiation, and he goes, since on our way to Mars, this is on our way to Mars, and while on Mars, but before presumably we build anything underground, they will be exposed to a lot of radiation during this period because of the lack of a magnetic field on Mars, as well as just the fact of getting to Mars from the spaceship. He's asking, does the inverse square law help us out here? And would radiation absorbing materials like lead be used in suits and spacecraft to combat this issue? This may be a little outside of what you guys are thinking about, but are you considering those environments of getting people to Mars while they're en route and before they establish the colony in full?
Well, lead is heavy, and what's its use other than just to stand in the way? So water is that has plenty of uses as radiation protection in space, and certainly regolith overcoat. Now, let me give an analogy, and I think this will help. I hope it helps. If the hotel is already there, then a fast transit to there and all the stuff is already there seems like a much safer and sustaining case than nothing's there and you've got to bring everything with you and everything has to go flawless. So one thing that I'm looking at, and I think DR is as well, is how can we get there quicker? But we've already pre-positioned, have everything up and running already on the surface so that the exposure of the astronauts to radiation and microgravity is minimized to the most, the best possible extent. So if we could do a fast transit from cislunar or Earth, get there quickly, get down quickly, where we know on the surface the GCR count is about 40% of what it is in space. Now we have an opportunity for the crew to actually survive, not lose any crew, and actually create a sustainable architecture from the start, from the standpoint that we did provide something in the wilderness. It's a pioneering satellite or colony or whatever you want to call it.
I imagine those back in Canada, back in the beaver trapper days, the Canadian, there would always be these trapping stations, just kind of set up for people that they could use while the weather got bad. It's kind of like that, but except heavily fortified, right?
Right. So again, if you look at it from the standpoint that if you can put enough stuff there and then the astronauts can go quickly there, get down as quickly as possible, get into a safe situation, stay there as long as necessary, and if they want to come back fast. And that would help. If we can come up with an architecture that we can afford to do just that, then I think we're heading in the right direction.
I think you're right. And with that,
sorry.
Go ahead, DR. No, go ahead.
Well, that's been a big emphasis of our more recent efforts on the transportation system and the overall architecture is to mitigate safety. We talk safety, but
Elon Musk doesn't.
We kind of just assume, well, landing on Mars is going to be, it's going to be a challenge. It's going to be unsafe. I think it's up to us to do everything that we can beforehand to provide a safe environment for the crew, whether it be radiation protection, putting in place habitats that are protected to get them there fast, to limit their exposure during the interplanetary transfers, and as well as trying to provide them an entry and landing that is as safe as possible, because that is a very hazardous event.
Yeah, we didn't get a chance to talk about the landing part of it, but yeah, you're right. I mean, I like the idea of setting up these automated systems to go out there, build all the stuff first so that you can, as Bob says, rush out there, get there quick, hide it, get into your shelters as quickly as possible. I also like the idea of creative uses of water as shielding as well. That's a pretty cool idea. Phil Daggins is also commenting, the way I understand it, the danger presented from the sun or cosmic rays is in the form of high energy particles, so inverse square law doesn't matter. Might be wrong though. Yeah, the inverse square law doesn't really play in here because Mars, we already know, is a pretty radiation filled environment as is, and so you need to have the protection when you get there as well as en route. They're thinking about this stuff, and so that's the good thing. And so I really want to thank you guys for taking time out. Let's see, Greg Gavro, sorry if I pronounced it wrong. Finally being on time to join chat. Too bad I had nothing to add. So well, I just added it. So there you go, Greg. You're now in our hangout. Larry Keese, I would think that the thin atmosphere and lack of magnetic field will present problems with radiation. Yes, it does. But they're thinking about it, and they know about these are known issues, and they're working really hard to get them done. The first boot steps on Mars, who knows when they're going to happen, how they're going to happen. But the good news here, and what you've learned in this hangout, is that we've got really good people working on these problems and thinking ahead so that whatever we decide to do to Mars, we're going to be ready to go. And these guys, I want to thank Bob Moses and Dr. Komar for taking time out to talk to us about these questions. I agree with you guys. I think the way to do it is the long-term view. Let's get serious about it. Forget this Apollo stuff. Let's go to Mars over the long term. Let's do it right. Let's stay there. Let's don't trash it. And let's set up a colony there. And I think they should call it Darnellville. I'm just gonna put that out there. I know that. Harleyville, Harleyville sounds better. I suppose. Harleyville.
Well, I mean, if we have multiple settlements, we can all get one named for us, right?
That's true, but somehow I have the. You know who I think is going to get the first name is Neil Armstrong. I think he gets one. I guess he gets one named after him too. We should get name. NASA should sell naming rights. That's what you do. And we got it. I just paid for the space program right there. All they have to do is sell the naming rights to the future Mars colonies, just like they do football stadiums. And boom, we're on Mars. We are there. You hear that, Harley?
Got it. I wrote it down. I won't tell you what I do.
Sell the naming rights, and they will. Hundreds of millions of dollars will be made in one fell swoop. And then the more colonies you have, the more money you got. So there you go. All right, folks. I want to thank you very much. Thank you, Bob. Listen, this has been a great hangout. Thank you, Bob, for participating not only in that chat last month but agreeing to come on and getting DR here. You guys were awesome. Thank you both so much for taking time out to talk to us about getting to Mars. Yeah, good. Well, hope you'll come back because we got a lot more to talk about. Are you guys having more meetings? Where are you guys going from here? What do you do now? I mean, what's next?
Well, DR, you want to take that one?
Well, I can go ahead. I think Bob alluded to some of the work that he's funded to do. I have some low-level effort from our center and directorate that is going to continue to investigate these ideas. But we're really hoping that the products of those can feed into the strategic decision process for our next administration and beyond, and kind of maybe turn the tide a little bit in the direction of looking at human exploration, not necessarily in terms of what's best just for science or exploration, but what's best for mankind in the in the long haul.
Yeah, exactly. And I know Harley, what I'm hoping we can do is get somebody here who can tell us they've got a lot of great people working on some really great issues. I would like to know what they're thinking about Mars and how they're going to approach it, because these questions need to be answered sooner rather than later, because I really want to know what NASA's feeling is on this. I know they're constrained. I know they don't have a lot of money, but they got to pick it soon, right? I mean, 2030s sounds like a long way away, but we got to start this stuff now, right?
Yeah, but it isn't. Yeah, no. Loads of folks, including our two guests today, have been developing design scenarios and so on, and identifying, and really important, identifying the key technological capabilities that need to be developed. Some we'll talk about today, and telling NASA headquarters, and telling Congress, and telling the White House, and so on. This is what needs to be done.
All right. So hopefully we'll have somebody.
If you want to go Mars.
Yes. Hopefully we'll have somebody on our Hangouts who can answer some of those questions for us, because we've got a lot of great people doing a lot of great work, and I want to see their work be put to good use. Okay, folks, I'm a little over. I went 6 minutes over. I'm sorry, but I love this topic and I love my guests, so I just went over a little bit. I hope you'll join us next week. We've got a afternoon Astro Coffee with Carol Christian. She'll be back, and we're going to be talking about comet swarms or an alien megastructure. You know that star KIC 8462852? Of course you do. It's that one where there might have been like a Dyson sphere around it, or people were thinking all kind of weird stuff. Well, we're going to have people who've been looking. It was discovered from the Kepler mission. We're going to have people who've been looking at this. We'll have people from the SETI Institute and others online to talk about this. So join us next Thursday at 3 o'clock Eastern time, as we always are. And Harley, we got another one on it. Happy New Year, everybody. Thank you all for joining, and thank you, Bob. Thank you, Kate DR. I hope you'll come back.
Yes.
All right, good.
Very much. Appreciate it.
Okay,
thank
so
you.
you're very
Take
welcome.
care, guys.
All righty. On behalf of,
I did not bring our rubber ducky with me to.
you didn't bring it to the AAS.
to
Oh
Texas.
my God! No wonder. Oh my gosh! You're not going to get anything done. All right.
Well, but I see that Bob's already. Oh, there we go. What's that?
Marvin
Oh, it's
the
the
Martian.
Martian.
Yes, outstanding. Definitely. That'll be one of the statues to be erected.
I'm afraid so.
Great. All right, folks. On behalf of Harley Thronson and Alberto Conti, who's also at the meeting, but could not make it. Thank you all for watching, and as always, keep looking up.
Looking up. Take care, guys.